record on this one and the share this one. Okay, that's good. And then later on, I want to pull out that homework a little bit. It's not in a, I think I clean this up certain way because up to here, 1, 2, 3, 4, 5. This is not, this shouldn't, this is, yeah, this is one starting from here. These are just like a general description, but we are supposed to do. We did that when we converted this into BMI, gender, see, this one sex into gender, it should be gender, diabetes 2 to diabetes, see, XRNA, see, that means exercise. And all of these one, even the general health, but these all the variables are kept, and it should start from here. So in order to, yeah, see, it should go like this. Question number 1, 20 points, A, B, C, under C, 1, 2, 3, 4, and D. And the 226 points, that means based on that one, you're going to fill this.
Professor,
Uh-huh.
for I was looking at question 1 today, and then when we do the hand calculation for the chi-squared, how do we produce the observed versus expected table in SAS?
Oh, okay, I'll show you. Okay, don't worry, I'll show you.
Thank you, Professor.
Okay, I'll show you. Yeah, this one. No, sorry, it's, yeah, sorry. Yeah, this one. Yeah, show you a hand calculation of PS and chi-square statistics. Chi-square for testing, where there's an association between the sex and exercise. Based on your calculate chi-square, then you can get this done even by running this procedure frequency, and along with the other necessary that function, then you can get that one too, the value. But we want you to do that one by hand. Then null hypothesis, this. And the number 26, create table 1 for the subject. You can use this table to complete this one. And write the results in that one is, that's another question. I hope that you have the pretty much a similar way, that 26 point to create your table 1. And then write the results, mean like you're going to run and get the results and put this here. That's what they have. They both go together. You can use this table template to copy and paste into Excel and then complete this one. Write the result section for this table. Right?
So, Professor, for question 2, I've created that table, but for third question, are we supposed to, I mean, I didn't understand what to do in this
The
third
results,
question.
I mean, like, I think that pretty much the same thing. I think the way that they have worded, because I didn't write any of these are already been available when we were given to teach the class. Write the result, because there's no way that I cannot even easily change any of these. Because they were already set up. Okay, write the results section for this table. That means like they were pretty much expecting to just to put the results based on that, the numbers that we got from here. No, can you remember? You can run the 2 tables. One is that your BMI versus gender. The other one, the BMI versus exercise. And by looking at those 2, that we can complete this one. I think they both write the results together. It looks like that. That's the same thing. That's a kind of the same thing. That's kind of the same thing. Part question number 2. Yeah. Yeah, you that fill this in, and then you can write some kind of a what you can see from that one. Okay, what you can see from here. What are you going to see from the table? You can explain that one. I'll help for that one too. Okay, I'll show you what to do. Okay, that one. And the other one with the number 30, the point 34 point, this one. Then later on, we're going to suppress even the obesity. We have 2 and 3 put together, and then put 1 like that. And then based on that one, we're going to go this route. The odds ratio and the Risk ratio, those things we can talk about. We can write the confidence interval, then we can talk about the obesity. In this homework, we don't see that. Then we're going to talk about the Cochrane-Mantle, Heinzel, that the procedure. That one also we have to get it done by hand. Okay. Anyhow, let's go ahead and one by one have a look at it. This one. Okay. So we pretty much did some of them the other day, but I want to complete this one and jump into that home in class assignments and then give a clear idea what's going on. Okay. Let's homework one. We can remember we got the data, we have the data, we to here. And this all that categorical data we changed 1, 2, 3, we were changing to normal, overweight, obese. I put that one like a guideline because this is like a guideline. See, you see, use the raw variable BMI for cat and call it BMI. Just simply call BMI when we were trying to do BMI at the same time. I call that one guideline 1, and that one we can call now BMI instead of that underscore BMI for cat, normal, overweight, obese, 1, 2, 3. Okay. The guideline 2, the gender has been changed. They're going to tell us to that sex change to gender. The gender actually male. See, 0 and 1. Earlier we had the 1 and 2. Those two replace 2. And have you ever been like a guideline 3 that using the role of diabetes? Okay, whether you have a diabetes or not. Earlier we have 1 and 3 for that question because there's another question in between that one. You saw the other day. It's coming from the code book. If you go to the code book, you can see there's another one in between for that pregnant ladies, that another question over here. But that's why we have a 3 for now. Then in addition to 1, 2, 3, there are another 2, 2, because we don't need those. And later on we change that one. Guideline 4. Did you participate in any physical? You have a kind of a practice of writing that some comments over there in that when you're going to look at it, that one later on, that you're not going to have a clear idea what you're doing. So whether you have done the exercises, see, 1 and 0, like that. The question number 1, exercise by gender. So that's the one that we are trying to build up over here. So they say here. Then they say for the complete case analysis, restrict your sample based on the following condition. Age has to be 18 to 99 and keep all these, including general health and education as well. Education has a 6 level. Education has 6 level. We have to keep that one too, and this one to 1 to 5. Okay, let's see. That's what we did over here. See, where 18 age, 18, 19. This one we kept that one, diabetes 2. This one we kept education. See, from this one we're gonna do this based on that those variables. We're gonna do all the answers for the question. Okay. Procedures. This procedure frequently create 2 by 2 contingency table for exercise by gender. So exercise by gender, we put exercise by gender. Normally, question 1, 1, 1, 1. Okay, see, question 1. See, exercise by gender. So I have my data in that this temporary. I think I have to have a look at it. Just there's nothing over there. See? Okay, I had to. The data in. We have SAS data already. And from this one. Okay, then we got to go here, library. I got data already there. And I don't have that transport ID created, but it doesn't matter. We don't have to create over there because the already data in this one. Okay. So then it already came out. Go to the data. From there to here, I'm gonna data out, I'm going to put into work directory. Yeah, so we should mean this one now. See, TMP. So we don't have errors. Good. Okay, to go. Okay, question one is exercise by gender. Normally, when you're going to build up the like a contingency table, there are two types of variables. One is the response variable, the other one is the exposure. For the response variable, sometimes we're going to call the Y variable. The exposure variable, we're going to call the X variable. For the Y variable, sometimes we're going to call the dependent variable. The other variable that we're going to call the independent variable, X variable. And X variable, Y variable, we're going to call the endogenous variable. The other one exogenous. So then which one's going to go where? This is another way to look at it, that which variable go to column and which variable is going to go to the row. So when you have a two variables, see, the X and Y, this is the same discussion we built in up over here, the same thing that you saw last time in the previous class, the relationship between Y and X. So the X variable, we can say independent variable. I'm going to call the var for my convenience. This one we're going to call the dependent variable. Dependent var, or you can say the response variable. Well, this one sometimes we're going to call this one explanatory variable, regressor variable. Okay. Response variable, we're going to say or exposure variable. And this one we're going to say Y variable. Sometimes we're going to call the endogenous variable. This one exogenous. Endogenous variable. And this variable has, let's say this one for in example, which variable gonna go to that one? Independent variable gonna go over there. So when it's contingency table, rows they're gonna go to the rows in contingency table. See, you can say the row variable. See, another way to have a look at it. Row variable related to the contingency table. And this one gonna go to the column variable. We can call that one. In our example, then we're gonna get the exercise by exercise. We have two options, and then we have to go to the exercise by gender. See, let's run this one and see what's gonna happen. Okay. Exercise independent. First row, see, independent variable exercise. See, by gender, the way that it's been that the given, okay, exercise by gender. See. See. So if you put this one there, but see how that this exercise based on the gender, then how could you gonna explain this one? See, how could you gonna explain this one? Explain through this way. Most of the time, you do exercise the male and female who are not doing exercise, female who are the male who are not doing exercise. They both are doing exercise. See here. Here both are doing exercise. Here, see, this female doing exercise. See? These are not doing exercise. They're doing exercise. Okay. And have a look at that. So then here that the way that see this one, see 0 and 1, see 4 variables, see row variable, if you put the exercise as an example, for this one example, you can put the gender. You can 0, 1. Here the same thing, 0 and 1. Okay. So see, that's the same thing we're going to put into the contingency table later. That's how the contingency table is built up. Okay. So now you can see here, the contingency table, you're going to see that, see, these are, see, frequency, how many, those are called cell frequency. This number called the cell frequency. How many people, how many female not doing exercise, how many people doing exercise, how many male doing not doing exercise, how many female not doing exercise. See? Those are frequency. That's called the frequency and cell frequency. Later on, cell frequency divided by the total, called the percentage. Then the row percentage. Row percentage means this number has been divided by its own total. See? See? This way. This total divided by the row total. Okay. So the other one, that there's a column total. Column total this way. Okay. The total has been divided by this total. That's the one. If you don't like that one, you can simply that see, I don't need that one. See, you can put this number. See, size by gender. See, you don't need that one. You can simply say that I don't need that one. See, I don't need the percentage. See? Right. See, that's the sequence. So the frequency is only either way is fine. See? So you can it and without. And without. Okay. Sorry. So don't need this one. Part B. See the observed and expected frequency. Then part B. Let's have a look at it. The part B. Part B. Part B. Show the clock out which show only the counts in each cell. See that's how they say the. I'm sorry. It's in part A. Now in part A. Part A, you have to show only the same thing that I have put over here. Part A. So part A. That is part A. Part A, I think I get. Copy over here. This is I'm gonna put. Oops, no. Accident. Okay, this one. Okay. This one. And B is the one that B part B. B show your hand calculation the Pearson chi-square 36 chi-square for the testing whether there's an association between the sex and exercise. See? So see the observed and expected frequency table will show the observed and expected cell count, where the expected count is based on the formula. How do you find the expected counted? You go to the row total, you go to the column total divided by the n. See? Row total and column total divided by n will give you the expected value. Then you have observed value, then you have expected value. See, then those two, you know, subtract n square divided by the expected value give you the this called the standardized. See, standardized error. Actually, error has been squared. See, this is called in another way mean squared error. See, you're gonna square that one. So, see, that's showing. How could you gonna get this number? This the observed value. This observed value. So it's our expected value. How do you get the expected value? This value, see, 111,531 times this one, 162 times 430 for that cell, for that particular cell. I'm here. See, I go to the row total related to that guy, and I go to the column total related to that one. I'm going to multiply those two. 111 times 531, 162, 430, and divided by this one. Okay, so let's see that. Sorry, here. Let's say that. Okay, that's for one. I'm going to show you that how to get the expected value. 111, 531. 531 times 162, 430, divided by 413, 748, 43, 785, 785. So we go to this cell. Table 01, 01. I'm going to show the table when I the gender. Zero one. This time we have exercise, and then 39, 20, 424, 72, 72, 107, 12, 3006, 179211, 15, 131, 30, 22, 17, 013, 748, 25, 1318, 116, 2430. So see, like that. So if you want to, these are for the observed values. So if you need that expected value, let's say that expected value, see, expected values 0, 1, see this for the gender, 0, 1 for exercise. Then let's say this cell, how do you find? See, this number, see, to related to that number, see. So you're gonna go ahead and get this guy, 111, see, 111, 531 times corresponding row total times the column total, which is 1,62430 divided by the grand total 413748. You do the same thing like that. So if you want this one, this cell, then you're gonna get this number times this number divided by that will give you that cell like that. If you keep doing like that for that, if you want the expected value for this one, then you're gonna get its total correspond to that row total times corresponding column total, multiply together and divide by the grand total. For this one, go to the grand total, the column row total times its column total. This one, these two multiply together and divide by that. So that's how you get these numbers. And you're gonna find its difference. See? This minus that, go to each cell. This is one cell, this is another cell, it's another cell, another cell. See? See? So you get these two to add 162,430. If you go to the expected value, again 162,430. And observed value, see, like this. But if you add 251,318, but if you go to the expected value correspond to that cell and the other cell, this is called the 3, 1, 1, 1, 2, 2, 1, 2, 2 cells. See? 1, 2, 3, 4. Some people put A, B, C, D. But anyhow, see, summation the same thing. Then you're going to get the difference between those two, call the error. See, 39,422 and square divided by its and expected value. It's corresponding expected value, corresponding expected plus. Then go to the next one, next cell. This minus that square divided by its corresponding expected value plus. Then go to this one. Okay. Take the difference between these two, square divided by its corresponding expected value. And go over here. Okay. Take the difference between these two, expected and observed value, and square and divided by the expected. That will give you the chi-squared value. This is a chi-squared value. This same chi-squared value you can see from that by running. Here you have to do by hand, see, like this, and you can get this verified. How? By running. See, if you go over here, see, this one like that. See, that's how you get it. See, and this minus that one. See, 979.01. Can you? How could you gonna get that one? See, if you run with the chi-square, see, chi-square, no rows, no percentage, no column percentage, no row percentage, no percentage inside that contingency table. If you want that, you can develop the mosaic plot. Okay, and on this one, that's this one. This is the mosaic plot. See, chi-square value, same thing. Chi-square value. Not only that, there are so many other ways you can run this one. For we cannot go through all of these. That when it depends on that when when the necessity arises, based on that one, we're gonna have a look at it. This one from systematically. In addition to that one, there are so many other ways to think, like root ratio chi-squared, continued adjustment has been given to the chi-square, the mantle housing, Heinzel chi-square, phi coefficient, contingency coefficient, Kramer's phi, like all these. And then if there's any failure in this test, you're going to jump into the Fisher's exact test as well. Okay, depends on the question, and then we can discuss, because otherwise that if you're trying to discuss about all this, that we gonna that miss the core part. Okay, so we'll stick to this one. See, you can get that one verified easily. 979.01. We pretty much got the same thing. Sorry. 979 by hand and by the code. Place. Okay, then that's that one. Okay, then what's the next question? Let's see the next one. Where's the other one? Yeah. Then Based on your calculation, this one. What is your null hypothesis? Your null hypothesis is nothing but you can say that you are trying to find out that relationship between those two. See? Null hypothesis, you can say. See? This one, 1b, 1b. One page calculation. Okay. See, based on your calculated chi-squares, you show your hand calculation for that B. C. Under C, see, what's your hypothesis? See, 1, 2, 3, 4. What's the significance level? This one is, this one should be, see. Okay, I'm gonna put here. Sorry. Oh. Okay. It should be 1. See, H naught. Exercise. Exercise and gender are independent, or there is no association between gender and exercise. Versus HA, alternative hypothesis, exercise and gender are not independent, or there is an association between gender and exercise. See, that's the conjectures. And what's the significance level? See, significance level is alpha. You know this has another name too. Size of the test. Size of the test. We have another name. See, 1 minus specificity. Another name. Size of the test, alpha, level of significance. Okay, third one. And then you're going to see that the critical value, then you have, how do you run the test? You compare and contrast whatever the value that you get from the chi-squared with its critical value. We had that discussion the other day. If you want, you can get the critical value without going to the table. You can get it like this. See, you can run and see. I'm going to get the chi-square tabs. I have to put the probability and degrees of freedom. Critical value. This one going to give C in 1 minus probability. It's going to give the area to the left. You have to give the area to the left with the along with the degrees of freedom. And I'm going to give the 0.05 and 1. It's going to come systematically read this. Probability is 0.01. 1 is degrees of freedom. Print pretty much everything like a probability degree. Pretty much everything like a probability degree. You want this one? 3.84. That's the same thing we saw yesterday from the table. But if the tables are unavailable, you can then find something like that. See in 1 minus probability degrees of freedom. See? So on the other hand, that if you wanted the probability, that then you have to give the value, sorry, the p-value, chi-square p-value. P-value 1 minus probability of chi-square. See, you have to give the chi value and degrees of freedom. I'm going to give 979.019 to that one and see what's my p-value would be. See. No, this one we don't need. Okay. And p-value. If you want, you can go to p-value. See, almost 0. So you know, based on p-value, you can say since we have a 0, that we can reject H naught. Or by comparing and contrasting this value, see, since observed chi-squared value, which is computed chi-squared value, which is 979.01, is greater than the critical chi-squared value, which is 3.841, which I got it from here, we can reject the null hypothesis. Or you can simply say, see, or can say since since p-value is the probability extreme than the observed value. P-value is what? Probability of chi-square value extreme, then it's absurd value. You know that we had this discussion last year, okay, which is 0, which is 0, okay, which is 0, we can say, we can reject the null hypothesis. The probability of, I'm sorry, probability that the chi-square, chi-square value screen, then it's absurd value. See, we can reject that now. That means there's a, see, there's an association between those two. There's an association between two. That's the same discussion we built up. Can you remember in a regression? These are kind of like a regression, but here that you have one on y-axis, the other one on x-axis, you're gonna see the relationship in through a contingency table. We cannot use the other method over here. We don't have any proper mechanism yet. We cannot remember in regression that if you have a continuous variable here, mainly here, regardless of the having a curve that not having a continuous variable here, not continuous means like a quantitative variable. If you have a quantitative variable here, let's say that thumb length being explained by height, see, then you have a scatter plot. Then you get the straight line gonna go through that one, and with that one you built up the relationship between these two, y and x. Y is as a function of x. That one, before we're gonna go to that kind of a mechanism in the primary stage, instead of going to that one, since we are working with the categorical versus categorical, we are using the contingency table. But later on, we're gonna think those are very the basic that the procedures. That's why we're going to go to very advanced method called the logistic regression later on. The reason is we might going to have a sometimes this one only that categorical. This one may be quantitative. If that's the case, you cannot tackle with the contingency table. Oh, it's a mixture on for the x. Well, there are so many x variables in a multiple kind of like a regression. But here still two options. Here you get the two options rather than the numbers. You have a height. You're gonna say yes, no, on, off, like that. Hired, not hired, admitted, not admitted, like that. See, but here the variables may be any kind. If any kind, continuous or categorical. Those variables can then explain. If it is a mixture, not with the contingency table, then you have to use the logistic regression. We're going to move on to that one later. Then later, again, instead of having this one, these two, we call it dichotomous. Dichotomous is two options. There might be several options for y-axis, y variable. Then we're going to say polytomous regression. We go to that. Those are the major three topics we cover in this class. Because it's like a vast, huge, massive area, because these categorical data analytics involved with more theory, more procedures than continuous one. It's like a discrete like a discrete math. People don't like to do discrete math, like to do the continuous and discrete math heavy. Okay, then same way the discrete probabilities in statistics heavy. Continuous one easy. Okay, the same way here in the primary stage, 2 by 2. You see, 2 by 2 contingency table can be utilized. Okay, that's the same discussion we are building up over here. So then question number 2. This systematically adds some kind of a confounder. Okay, let's see that. What they say. Do you hand calculate chi-square procedure, include the relevant procedure, put in explain. Do you one hand calculator chi-square statistics and 2 conclusion on the presence of an SMS that produced by the this one? Yes, you saw that one, hand calculated one, and then everything very same thing. Include the relevant procedure frequent output in your explanation. Okay. Then what? Then 2, then 3. For this objective, you can use this table template, copy and paste into this one. For this one, now you have to complete this one. In order to do this one, the 20 points, these points are to get the run this one, okay? Run, okay? Run the appropriate code in order to get this done. Number 2. Let's go to number 2. Question number 2. Number 4. Why is number 4? Yes, number 2. Number 2. Oh, yeah. Let's see here. Number 2. See, confound us by the exposure. See, we go to same thing now. Tables, exercise, and gender. See, being explained by BMI. That this means what? Exercise being explained by BMI, gender being explained by BMI. See, exercise versus BMI, gender versus BMI. If you put this to the front, BMI versus exercise, BMI is a gender. If you take this out and put this one, sorry, take out the parentheses and put the multiplication, that means you go to the exercise, and exercise for a given exercise is going to be that stratified. Stratified means like for the given level of this one, these two will be checked. For the given next level, these two will be checked. We have that kind of a question in question number 4. Okay. So, but here we're going to do this versus that, that versus that, not the levels. This other one called the stratified contingency table. Okay. This one. Let's run the for number 2. Number 2. See, you get the BMI versus exercise. See, body mass index and see, and versus the see, BMI versus the gender. See, how the data BMI gonna change? See, you can see this one here. The male, so say female, male. Here whether you do exercise, not doing exercise, how the BMI has been seen. So exercise and BMI. So exercise come first. So x-axis and y-axis. X-axis and y-axis. That's why x-axis, x1s are go to the x-axis. We normally call those variables are row variables. No? See, row variables, column variables. See? So you can easily see that one. See? So, see? From this one, by getting all the numbers, you can fill this out. The one that I showed you earlier. Yeah, we can fill this out. Let's see. First, we'll get that one, and then later on fill this out, and then write some description. Okay, so let's go. Before that one, let's see that whether they have the same thing. Okay, 164. See, get the numbers. Then you need the percentages. That's how we get the percentages. First one, see, this is a BMI, population normal, overweight. Sorry, I'm sorry. Yeah, population normal, overweight, and obese. So normal, normal, obese, overweight. Why they mix up here? That's interesting. Why is that? Normal, obese. Then what how we call? Yeah, no. The 2 is overweight. The third one is obese. Why do we have the same problem? Number 2, 3. With a mix up or what? One, two, three. Doesn't matter. Okay, that doesn't matter. Okay. You see, they were like the normal. So when you're gonna fill in this table, you have to be careful. Yeah. So, but they have given that one. See, for the normal versus male, normal versus male. Then 43061 male. Let me see the code. I had to go and see the code. Earlier, one becomes 0. Okay, male. Okay, female is just 1. Okay, good. Okay, this is female. This is male. This is female. This is male. This is female. Then we can see that normal and male. Normal and male. See, fill this out. 43061. 43061. Then obese and male. Obese and male 46764. Doesn't matter wherever it is, but make sure that you're going to put to the right the cell 46764. And their corresponding percentage. Okay, then that one 46764. And for the female, we do the same thing for female. See, 10, 100, 2,291, 100 to see 291, 69, 851, 69, 851 for that obese. The other one 79, 176, 79, 176, 72, 605. This number come here for the overweight. Then there, see, all the males total 162. See, this way in this table. See, 162,430. See, 251. This one, and their percentages 39.3. See, as a percentage or as a decimal, you can put the percentage 39.3. This one 66.7, like that. See, you can, by looking at this one, you can figure this out. Okay, you can figure this out. So then the p-value is based on the Pearson chi-square test of association. See, based on the chi-square test. The p-value. Can you remember we got the p-value earlier? Certain way. Where is the p-value? Where is the p-value related to this one? See, female. See, female with what? Female and the male. This one, gender and male. See, this one, overweight. See, sorry, I'm sorry. The BMI. BMI versus gender is the p-value. BMI versus exercise. This is the p-value. How did you get that one? When you run that p-values, do you see the p-values here? Yeah, see that p-value. So the other p-value, see, gender by BMI. See, that's how you get the p-value. Okay. So this one, gender by BM by gender. From that one, those table you're going to utilize to when you're going to talk about the BMI versus gender. See, BMI versus gender related to that one. This is the chi-square test. You can get this done by hand, plus you can get the probability and both by hand or by through this one. This is the p-value. See, as the p-value comes here. And the other one, BMI versus, I'm sorry, gender. This one, I'm sorry, gender. This one, that's the same thing. P-value. Okay, this p-value. This one, gender versus BMI versus exercise. BMI versus exercise, and put over here. Come on to these both of them. Like this. So your table should be like this. You can talk about that. I think note that the table one is all about the exposure variable. Exposure variable means variable and it's not the exposure variable. That should be response variable because this is the exposure variable. Okay. And it's read from the top down. See, For example, of those with the normal, the 29.6 are male, which are fewer than what we would expect based on the distribution of male in the population. It's like some kind of a, whatever you saw from there, that you can give a writer some kind of a description. Okay, you can explain this table like that. Okay. Then, but that's that one. Then number 4. Let's go to number 4. Number 4. But the number 4 is waiting for. See, it's number 4. Look, consider simple model. See, now we are trying to go through this route now. You're gonna say diabetes can be explained through the obesity as well as gender now. Rather than earlier we talk about the diabetes and obesity only, like that one. See, y versus x, 1x only. Now there are 2x. One variable may be something hidden variable, lurking variable, confounding variable, because they can be hiding and then gonna affect to the variation of the diabetes explained by the obesity sometimes. That's the discussion we are trying to build over here. See? That's the discussion we try to build over. That's determine the explain if sex is a confounding variable, whether this is a modifier, effect modifier, like that. That discussion we are building up over here. So here, instead of here, what we had in the beginning, see, gender versus exercise versus gender, or gender versus exercise. See? Either way, you can get the either way, but based on the way that how you have that set up that one, you can then talk about that one. Okay, so that makes sense that if you put that exercise to y and gender to x, okay, either way is fine. Either way is fine, but okay, but that's okay. Either way is fine over here, but here we're gonna expand our discussion to 2 variables, 2 x values. See, x1 and x2, and this is diabetes. But this is the one we are trying to explain through the logistic regression later. I'm not going to go there now because they don't ask anything on logistic regression at this stage. Diabetes. See? So they're going to ask about, see, diabetes. Can be explained by obesity and gender? See, gender. It's a function. See, this is y. Y is a function of x1 and x2. Then how could you gonna write this one? See, this is the y. Beta naught plus beta 1, x1 plus beta 2, x2 plus error. That's the normal procedure of writing that one. But you cannot tackle that one for reason. This one is dichotomous. See? This one say this one has a 0 and 1. See? 0 and 1. See? Dichotomous. These are regression coefficients. Regression coefficients, beta 1, beta 2. They to be estimated. See coefficient. 3 coefficients over here. These are, we can say, regressive variable. Okay. Explanatory variable, regressive variable. Regressive bar. Okay. Regressive variable. Sorry. Yeah. Okay. Dichotomous. Earlier that you, in the previous class, you explained this one if it is continuous. Now you cannot. That's why you move on to different things, because this behave. Earlier, you learned that y behave as a normal distribution. You can remember in the beginning. Now not like that. Now behave y like what? Either this one or this one. See, either 0 or 1. See? Then you have to find the probability when y equals 0. Then you have to find the probability y equals 1. Probability because y equals 1, probability when equals y equals 0. That kind of a discussion built up in a dichotomous situation, which is called binomial. This is go through a binomial distribution. Since binomial distribution, these equation you cannot tackle like this way. That's why we're going to rearrange this one. and then bring it to like a logistic regression format. Regression format. See, here you have x1 here, another one x2 here. See, like that doesn't matter. See. X1 you can talk about the obesity. See, this one gender, and this one y is your response variable, which is diabetes. If you have a something like that, we used to draw like a plane, not a line, because of the 2-3 dimension. But here we don't go to the plane. We tackle this one in a different way. Okay, we're gonna bring this one to a different way we tackle this one. Okay, so this fitting into what? Probability y equals 1. It's a normal. Each and every individual, you go ahead and check and see. Each and every individual we're going to call the trial. See, now each trial, see, each trial, see, this is called each trial. Trial means each subject or individual. Individual, either you get yes, sorry, 1 or 0. 1 or 0, you have value. See, 1 or 0. See, and then you can say the probability when y equals 1. Simply, I'm going to call it a simple p. This one probability when y equals 0, I'm going to call that one q. P plus q always 1. Q is nothing but 1 minus p. This one called the success. This one called the failure. Then you can see how many number of people, number of subjects. See, you can get some kind of variable. See, no, I'm gonna say use z, number of people have diabetes. See, z. That's the case. This can be denoted by binomial. This is how we're gonna write like this. N means sample size. Sample size. Because of that reason, we're gonna do the changes to this guy. That changes we're gonna talk about later. For time being, we're gonna see that's the same thing. And later on, we're gonna see whether this guy is a hidden variable, lurking variable, confounding variable, or this here effect modifier. See, like that. See? So let's say that we have to do some kind of arrangement over here that between the sex and obesity by first creating the binary variable obesity. See, bring this down to earlier we have 3 categories, now 2 categories. BM4, 2 and 3 put together and then make 1. So let's do that one first. Okay. Let's do that one first. Okay. So number 4. New guideline for BMI data temp. Okay, I'm gonna call this time temp, TEMP. I bring the data. Obesity. Obesity 0 and 1 both. See, either BMI 4 category 2 and 3 put together. See, BMI 4 equals 1, then 0. BMI 4 in 2 and 3, then put to the obesity 1. See, it's called the obesity 1. See, right there. Guideline this on diabetes 1 and 3 as usual. That the gender as usual. Little bit we run this one. Okay, obesity is the one we change. Oh. What happened? Oops. New variable obesity we taken into account. Diabetes, obesity we change. Earlier we called BMI, now we call the obesity. Okay. Earlier we called BMI, same thing. Now being little bit condensed, and 1 and 3 put together, normal and obese put together, and compare with the overweight. Okay. That one. Okay. See. Then what are you gonna do? See. You see. Okay, if you want, you can sort this out too. A, part A. Let's look at the part A, what they were looking for. 2x2 contingent table between diabetes and your new variable obesity. See, diabetes and obesity. So you know for sure that obesity is in X, okay, X here, and diabetes is a Y variable, one of the Y variable. Then it should gonna go to what? Columns. This gonna go to rows. Okay. So let's run that one. So see, obesity come first, diabetes no rows. Whether obesity or not, see, you get to see they were not obese, but they get the diabetes. Some people no, yes, but yes, no too. See, see, they are obese, but they're gonna get the diabetes. See? That's a contingency table we are looking for. And part B, what? Show you a hand calculation of the odds ratio. I'm sorry, odds ratio for a diagnosis diabetes with respect to the obesity and interpret. Show you a hand calculation of that OR confidence interval and interpret in terms of it. Determine and explain if the OR is statistically significant. See, odds ratio. Before you go to the odds ratio in this particular table, you have to talk about that odds. Which odds that they can talking about. See, in this table, see. Stable. So let's a little bit talk about the odds on that. So over here, see. This one clearly, okay. So that if I show you this one. See, the basic size contingent table is 2x2. Summarize the counts, frequencies for combination of the row and column variable. The column variable is typically the variable of the of mean interest. See, sorry, main interest outcome or endogenous. The row variable is basically the effect the outcome variable called the exposure. That X is the outcome. And odds, see the strength of an association between two variables, diabetes and this one, can also be measured by the odds ratio and the relative concept of a related concept of relative risk. These two, odds ratio and relative risk, odds ratio OR, relative risk RR, we're going to utilize to that talk about the strength of the association. In that regular regression, we use the R squared. Can you remember? Correlation coefficient, or its square. Coefficient of determination, you can remember. Mainly the correlation coefficient. Here we are using what? In order to check that their strength, or whether their strength, okay, can be determined by the odds ratio. So I'm going to put these numbers in 1, 1, in 1, 2, see, 0, 1, 0, 1. For the diabetes, no yes, in 1, 1, 1, 2. And the row total, I'm going to put 1 dot. And 2, 1, 2, 2. Second row, 2 dot means that's a total. And this one, column total, dot 1, this one, dot 2, this is a grand total. Okay. That's the grand total. So let's see that how to calculate the odds. See, the odds of the non-obesity causing non-diabetes. See, 0 to 0. Can you remember? N1, 1 divided by N1, 2. See, non-obesity. That means that you're going to talk about the table. error is there. Okay. So this one, see the odds of the non-obesity. Non-obesity. See, non-obesity causing non-diabetes. Causing non-diabetes. See, if you not obese and no diabetes as well. See, this one. See, see. Non-obesity causing non-diabetes. That odds. See, that odds. See, N11 divided by N12. So see, that's called the occurrence, and this called the non-occurrence. Okay. Occurrence divided probability of occurrence divided by the probability of non-occurrence called the odds. Okay, so I'm going to write here the probability of occurrence. Okay, probability of occurrence event, occurrence of event, E event I'm going to call E. Okay, non-occurrence. These are probabilities. The probability. Odds of an event E. Odds of an event E is the probability of occurrence of event E divided by the non-occurrence. So the same way they were talking about the thing. If somebody is see, if they were not obese, what's the probability of not getting that one is getting diabetes to not getting diabetes. See, getting diabetes, not getting diabetes. If since it's a probability divided by probability, you can forget about the n get cancelled off. That's why see normally the probability you have to write n11 divided by simple n divided by n12 divided by nn. Those nn get cancelled off. That's why we just write like this. So simply this divide by that. If you're interested in this odds. So in similar fashion, if you're interested in this odds, 1, 2 divided by n1, 1. See? 2, 1. 2, 1 divided by this guy divided by that guy. Those any odds that you can look into. Normally that in the gamblers, they are going by the odds, not by the probability. See, it's a ratio of the probability. Ratio between probability called the odds. So, but for the diagnosis of a diabetes with the with respect to this one, obesity, we simply calculate this one. But for the diagnosis of diabetes, see, this one, this is what I'm interested in. See? With respect to obesity, whether you are obese or not, see? Obese or not. Those two are the one that I'm interested in. See? 012, 012, see? Whether see diabetes with respect to obesity, see, that one is n12 divided by n11. Okay, n12 divided by n11 means its probability divided by non-occurrence probability. This is another way to write it. And then the non-obese, see, with respect to obese or non-obese, see, non-obese, see, odd of the observing that see, see, the odds of the non-obesity causing diabetes, the odds of the obesity causing diabetes, those two, I'm going to calculate. That means n12 divided by n11 and n22 divided by n21. And that ratio called the odds ratio. Odds ratio. So if you simplify, you get the n2, n1, n22. See? See? Occurrence to non-occurrence. This is the cause. This is the reason. This is that condition. Like that, you can look at that way. This is the condition. Why? X will be that what causes that one to get that particular condition. Okay, like that. So when you simplify, you get the n22 divided by n21. N22 means this one divided by this one. See, n11 divided by n1. See, 022 divided by 012. This ratio divided by this ratio. What's ratio? That's called the this one. Then you can simply, we have those numbers. You're gonna plug in over there. Those numbers we have. We have 46018. See, 1, 2, 46018. See, these numbers, all the numbers. This is N11, N12. See, N21, N22. See, you're gonna plug in this one, then you get the 3.4053 OR. See? But they need this one to be done by the hand. So do you see that one anywhere in this printer? See? Do you see that one? See? Let's run this one for 3.4053. We got that one. You can easily get that one, but the way that this question being structured, they want to push you to that, do this one by hand. That's what they are planning to do. 3.4053. We got that. You have to double check and see whether you are on the right track. You are using the right formula, because when you talk about the odds ratio, if you don't have any clue, it's not simply go to read this table. No, you cannot. You have to have a very clear-cut idea about all of these, whatever you produce at the end of the day. But that's the knowledge that we have built in up over here systematically, one by one. We cannot go through all of them because of the time constraint. Other than that, at the end of the day, you are highly expected to know that how to explain the whole that that report, everything. See? Your observation is, see? That's why we got that one. Then we're gonna look into its confidence interval. Why we have the confidence interval? Now we have a question here. Why? Sorry. Why we have a confidence interval? See, in order to write the because that, see, we can conclude that someone has obesity will have a thing. This is how that interpretation. We can conclude that someone has obesity will have 3.4 times the odds of having diabetes relative to someone who is not obese. So with respect to obese, that one, this side, and this odds compared with this odds for getting diabetes. See, what are the chances? What is the risk of getting the diabetes for the person who's obese is 3 times? See? Higher than that somebody who's not obese. Like that, we're going to talk about that with respect to that. This odds. And then you're going to go ahead and find the standard error. Standard error means standard deviation of this guy. This guy standard deviation, there's no formula. We have a LN. We have a LN. LN OR. I'm going to go to natural log OR is given by 1 over N11, 1 over N12, 1 over 21, 22. Write the confidence interval. Then you're going to plug in those values. You simplify. Once you simplify, you can write the confidence into a lower bound of OR, and this one is nothing but exponential ln OR. This OR means observed OR. You have only one OR. Now, with the aid of that one OR, we are expecting you to produce a whole bunch of OR. Okay, can we do that one? Yes, the theory has built up in such a way. You say that this is OR is not enough because that's based on your sample. If someone else have selected this for the same scenarios, the data, that particular OR not going to be the same as your one. And we got another one, another institute or person or institute or country or anything like that. Those are varying from that institute to institute, vary the individual to individual. That variation to be tackled. How? By giving this one called the estimate. This is actually an estimate for the OR. This is not OR. This is an estimate. See, this is an estimate. That's why we prefer to write this one with the hat. Actually, this with a hat. See, I'm gonna put hat over there. See, an estimate. See, an estimate. That means an estimate. All these are estimates. So these are called, see, that's a point estimate. See, I can say that point estimate of OR. Point estimate. Estimate of OR, which is OR hat. The other one is interval estimate of OR. That's the second category. First one, interval estimate. First one is a point estimate of OR hat. Second one is what? Interval. How do you get the interval? You have a lower bound for that guy, you have an upper bound. Then this should be what? Hat. This should be hat. Okay. This should be hat. This should be hat minus 1.96 times SC LNOR. See, SC LNOR is this one. When you plug in that one, you can easily get the lower and upper bound. See, upper bound is counterpart. See, plus sign, this one. Those are the one you're gonna see here related to that one. 3.3237. So they're gonna ask you to do that one by hand. Okay, you should do the by hand and compare and contrast and see whether you got the right answer. That's why you have to show the work like the way that I'm showing over here, exactly like that. I didn't put the number, but you can plug in the values over here and get simplify this one and plug in here, get the lower bound and get the again do the same thing. See here, you again OR estimate. Estimating that's the observed one based on the observed one. See? At you can calculate 3 point something. See? You get that one. You show that one upper bound and nicely you can write that. Then again you can write this one once you calculate everything. You can write confidence interval. What is the level? 0.95 confidence interval for OR is given by those two numbers put over here. Like that. Get the numbers. There's a kind of a, you should get it very close to the numbers that appear on this result. Yeah, 3.3237, 3.4889. Okay. So its counterpart is a relative risk. Relative risk is what? Instead of going for that risk that this divide by that or that divide by this, I'm gonna go to this and this divide by its grand total. That's called the risk. See, I'm gonna divide, see, probability. There's a probability. I'm gonna take the probability this time rather than odds. I'm gonna divide n1 to, see, if you want the 0, 0, this means that, see, 0 means that this 0 divided by this 0, see, this 0, given that this 0. See, this means that diabetes 0, this is obesity 0. Diabetes 0, you get the diabetes 0, given that you have obesity 0. That means this one, in 1 divided by its grand total. That's called the risk. That's a risk. Or you go to 1, 0. 1, 0 means diabetes 1, see, this one, given that you have a diabetes. You have this one, given that no obesity, this one. N1 to divide by N1. N1 see dot. And the other one 0 given 1. This line means probability of this called the conditional probability. So this one, see, this one. You have the same no diabetes given that obesity, which is 2, 1 divided by this one, 1, 1. You have that one, see, diabetes given that obese. And 2 divided by grand total. Earlier you did divide by this guy. Now you're going to divide by its grand total. That's the difference between the odds and risk. Okay. See, look at now. I'm going to consider this one. That means what? You don't have obesity. You have a disease. That risk. You have a obesity. You have a risk. So that ratio is called what? That ratio is referred to as the, see, normally that one is that, if I can show you that one, this one, you can call that one, see, if you explain that on the probability of obesity causing diabetes, see, probability of obesity is 1, this is also diabetes, see, the probability of obesity causing diabetes is how much? And 2 divided by its, this one, same thing. Diabetes and N2 divide by N2 dot. marginal total or total. See, that causing that one. The other one is probability of non-obesity causing diabetes. See, obesity you have, diabetes. Non-obesity, diabetes. See? Obesity causing diabetes. See, that one is in 1, 2, see. 150. You have a diabetes, this guy. So this guy and this guy. See? See? So that ratio is called what? Relative risk. So the ratio of these two probabilities. You have obesity causing diabetes. Non that you don't have obesity but causing diabetes. That ratio is called the relative risk. See? Once you get N22, N2 dot, N1 dot, N1, 2, then you're going to plug in the values. If you plug in the value, you should get the same answer as in relative risk. Okay, relative risk. Okay, now they have a go to the printout. Go to the printout. Then observe here. See, now you have a two types of relative risk. What that means, you do column 1 and column 2. Now I'm talking about column 1 here. See, you saw that one. I'm comparing column 1. See, I'm comparing column 1. See, somebody who is obese has a disease, diabetes. That probability or that relative risk divided by this risk, called the column 1, see, related to this column. Column 2, risk, relative risk. If you divide this one, somebody who has its counterpart, somebody who has a obesity but no diabetes versus somebody not obese, have no diabetes. That relative risk called the column 1 relative risk. That's why you get the relative risk here. Sorry, risk here. You know how to get the risk. N21 divided by N2 dot. You know how to get the risk here. N11 divided by N1 dot. And then divide this risk by that risk. Okay, that's called the relative risk for column 1. This is the column 2 one. That's why you have a 2 types. Okay, everything you can get it done by hand, plus that even the printout is going to produce that one. When we have a massive data, we don't go to like that, but we are training you that to read this printouts. Okay, so that's how see, if you go to that's the relative one. If I add that one to 2, you're gonna see that one down the road. Yeah, that's why you have 2 of them. See? And they are corresponding the confidence interval. You can get the confidence interval if based on what you are. That is a formula. This is the formula. See? Formula says standard error 1121 1121 1121. See, 1 over n11 1 over 21 1 over n1 dot 1 over n2. The mainly you are on what 1 1 and 2 1. That means you are mainly that's related to this one. Okay, this thing 1 1, sorry, 1 1 and 1 2 1 2 n1 n2 1 1 2 1, sorry, related to the 1 1. That means the column 1 relative risk. If you want a standard error for that one, 1 1, this one, and this one. Okay, in this formula. This formula that means simply 1 over n11. Okay. Okay. Related to that for the relative risk for the right here relative risk standard error for relative risk in column 1. This has been in column 1. That's why I say in 1 1 and 2 1, and there. See, this guy divided by that guy, that relative called the column 1 relative risk. This relative risk divided by this, sorry, this risk divided by this risk. for that relative risk for the second column. If this the standard that has been given over here for the first column, okay. So similar fashion that you can build up that one. Same thing like earlier. See, lower bound for RR, which is ln RR. Again, this one is again I have to tell you that this is an estimate. See, this is an estimate. See, RR. Same way in here. See, you can get the estimate. See. Once you plug in that one, see, like that. OR is typically for the retrospective studies or the case control studies. RR is typically for the prospective studies. Retrospective means past data. Data has already that recorded. Case control studies. See, prospective means for the future. Okay. Right now we do something prospective studies. The other one retrospective. OR using for the retrospective study. If the data available from the some kind of a previous research, you're going to go ahead and analyze that called the retrospective studies. Okay. So, but here one shot you have the answers. Okay. See, you can compare and contrast and see. Okay. Contrast and see. That's that one. And the OR confidence interval, you know how to do. Determine and explain if the OR is statistically significant. OR is statistically significant. How could you going to figure out OR is statistically significant? You have to see OR gonna be within that what? That your zero value. There's no OR versus there's that statistical significance come when you're gonna run the test for OR. See? When you run for OR, see what that means. What that means? That means, let's say that this kind of a discussion we have built up pretty much all the time. See, you can say that, see H naught, H naught is OR, so 0 versus HA OR not equal 0. See? Then what? You have what? You have a confidence interval for OR. Already you built up. You know that confidence interval. See, if the hypothesized, another way to that run the test, decision rule. It's a third method. So far you learn p-value method. Then you use that comparing observed value and the critical value method. This is another method. Decision rule is the hypothesized OR, which is 0, is outside the confidence interval of OR. We then reject H naught. You reject H naught. You check and see whether your hypothesized value inside or outside. If reject H naught and infer that the test is significant. You can check that. One way to check. That's like we're going to build the confidence interval. It's a testing. Two-tailed test. See, we assume that ln OR normally distributed. We're going to utilize that one with the data. That's why we put the 1.96. It's a two-tailed test. Two-tailed test. Why? Not equal sign. ln OR. Okay. Distributed, normally distributed. Okay. Normally distributed. We can assume that ln OR normally distributed. The center, ln OR center is nothing but ln OR observed value. And here you're gonna get the significant level, 0.95 is gonna be in the middle. The confidence region. This one what? Rejection region. This is a confidence region. That's a confidence interval going to be in the confidence region. It's a rejection region. Rejection region. Rejection region. Region. This is the value you got the C critical. Z value, critical value. That's the one we call the 1.96. Can you remember? And here too, you have a C. If it is C, okay, I'm going to convert this to Z, okay? I'm going to say Z of ln or, okay, it's easy like this. Z, C, critical is negative 1.96. Negative 1.9. That's why we put the 1.96 for our confidence interval for the critical value. Normally confidence interval is anything confidence interval is how do you write the confidence interval? You're going to write the confidence interval. Confidence interval for any parameter. Parameter means anything that you are interested in. Here you have the confidence level. Confidence level. Level is 1 minus alpha. You know alpha is 0.05. That's a 95. Any parameter is what? Point estimate of parameter. See? Plus or minus critical value times standard error of point estimate. These two together we're going to call the margin of error. MOE, which is called the maximum error that can incur. Max error. Max error. Plus or minus max error should be added to that one. Then later you're going to get the whole range of interval the estimates. That's called the interval estimates. Like that. Okay. That's the discussion in that one. See? Normally distributed. This means also distributed. Okay. Is distributed. This means tilde means is distributed. Like that. See? So then what? Now you're going to go to the PROC3 and then a 2x2 contingency table between diabetes and obesity, but one for female, one for male. It's not by the gender, but by gender, but it should be separate. Let's see how this can be done. Okay. One for male, one for female, because we are going in this route now. We are trying to do the Cochrane-Mantel, Heinzel, weighted average OR as well as relative risk, both we can build up. Okay. So I'm going to go head over here and go to 4. Okay. This time I'm going to put the gender times obesity times diabetes. Okay. If I want, I'm going to put the CMH2. CMH stands for Cochrane, Mantel, and then Heinzel. See, relative risk also can be displayed too. See. This one for, see, together. I'm sorry, here. Obesity, I'm sorry, obesity, diabetes versus obesity for gender one for female. See, female. See, okay, separated. It's not the within the gender one for the it's called the one stratum. That's called the one stratum or one level. See, these are stratified now. Stratified confidence, the contingency table. This one again, diabetes versus obesity, then gender for the female. See, you have both tables. See, this table and this table. See, that what they're gonna do, they're gonna average that one everything. Relative risk of that odds ratio, we're gonna average because since we have a two table and see whether the gender is playing a heavy role here. That's how you're gonna figure that out. That's how you're gonna figure that out. See, that's how you're gonna figure it out. So, okay. So the same thing that. Okay. So look at here. See, before you answer, see, I'm gonna. You see, Cochrane, Mantle, and Hansel equation to explain and adjust. See, this to explain and adjust for confounding, lurking. See, see, hidden, latent. See, variables. That's a confounding, such as gender in our example. We can use a stratified analysis in which we set up a series of 2 by 2 tables, series of 2 by 2 table based on how many levels you have for the gender or the hidden variable. Hidden variable here, the gender is the one we suspect whether it's going to play a heavy role underneath like that. Most of the cases, time factor is the hidden variable. You know that one. Time factor is a critical part. See, any of these discussion, if you include time factor and statistics become stochastic, it's heavy, very heavy. We have to handle that one very carefully. That one. But this is a very different discussion, that one. But here, see, 2 by 2 series of 2 by 2 table, one for each stratum. Stratum means in each category. In our case, for one for male, one for female. In our example of the confounding variable, suspected confounding variable. Having done that, we can compute a weighted average of the elements of the risk factor, risk ratios. See? Relative risk. See? Risk ratio or relative risk or odds ratio. Or, these are the risk ratio or relative risk. Relative risk or risk ratio, but the same abbreviation. Risk ratio, odds ratio. Same way, relative risk. Across the strata, the weighted average provides a measure of association that is adjusted for confounding. Because with the confounding, if it's going to come and affect to that one, that will produce a very serious issue at the end of the day. All the results going to be wrong at the end. That if it is going to heavily impact to us, but we thinking that it's come in and then come to the picture and then affect to that one. That's why here we can ask, at the end of the day, determine and explain if the gender is a confound variable or effect modifier. Confounding variable that changes all the results, but not the effect modifier. Effect modifier not going to change that one. Okay, that's why we have to have a bit of that discussion over here. So let's have a little bit look at it. You have to do some kind of adjustment for that one. For your convenience, the same thing that I had, but this time I put the A, B, C, D for your convenience. I'm going to say this outcome. See, outcome. This side we call the outcome. This side we call the risk. Okay, easy. That what the risk factor present, exposed. That the risk factor absent, unexplained. You know the risk factor is what is the risk factor? Our obesity, not obesity, obese. See, obese over here. Outcome is the diabetes. See, absent here. I put the absent here, present here, absent here. Okay, that's okay. Okay. But in the other table, you have a present here, absent here, but stick to this one and build up what you really want to build up. See, so anyhow, see, outcome present A, B, A plus B, C, D, C plus D, A, C, like blah, blah. Risk ratio, you know risk ratio, A divided by A plus B, see, A divided by its grand mean, the total, marginal total, see, divided by C divided by that one. Present, our risk factor, whether present or not. See, that's the ratio. You're going to go to the tackle whether you have that diabetes or not. Here diabetes, here not. Okay, diabetes, whether you obese or not. That ratio. See, that's the ratio that we wrote. Simplify and wrote. And the odd ratio is something like that. If you want A divided by B, you have that for a given you are obese. You have a diabetes or not diabetes. A divided by B. The other one, C divided by, look at the difference here. A divided by B here. Instead of A divided by B, I'm using A divided by A plus B. That's called the risk. That if you use the ratio between those two, called the risk ratio. Here, A divided by B, C divided by. Here, A divided by A plus B, C divided by C plus B. That's the same thing I used earlier N11, N12 like that. Only difference, I got the absent one here, present one here. Okay, but that doesn't matter. It's not a big deal. Now what are you gonna do? See, now you're gonna do the relative average. See, sorry, weighted average of the risk factor and the odds ratios are computed as follows. I'm gonna do this one for each and everybody, every table. See, I have now two tables, one for male, one for female. See, you have to do that one. One for male. You do this one for male, like this, exactly like this. And this one, see, like this for one. And then you sum up. Sum up means like you do that one for the female as well. Female as well. See. So in this case, see, where AI, BI, CI, DI are the cell frequency of the 2 by 2 table in the ith stratum of the confounding variable. Ith stratum means like a female one. You're gonna do this one for exactly whole thing for female table. And plus, you're gonna do the same thing for the male table and add them up, add them up, add them up. Then you're gonna get the relative risk for the that Cochran-Mantel-Haenszel estimate. That means it has been weighted. The primitive version, you do the same thing for the, if you need the OR, you do the same thing. AI, DI, NI, that for the female table, you go to here, see, this is what I'm talking about. You go to this table. This is your A female, A female, B female, C female, D female, like that. Okay. And the same way, this is for the male. See, this is for gender zero. That means this is A, simple A for that. A for male, B for male, C for male, D for male. So you plug in into these values. Okay, I want you to plug in into and then simplify. Okay. So I'm showing over here that because of the way I'm struggling with this time because of that reason. So I'm gonna little bit expand this one and show you. So if you plug in over here that A1, I'm gonna say with respect to that table, be very carefully get that one. When you're gonna go to the table, make sure that the way that how I put over here, A for that, see, follow the same way. A for outcome, see, outcome present, absent, okay? Present, absent, make sure that this one is, see, this table you have over here. Doesn't matter, you see, present 1, 0, this one 0, 1. Okay, see, 1, 0, 0, 1. That's how they put it. This factor, I'm sorry, 1, 1, I'm sorry. Respect to present 0, 0, flip. So obese, diabetes. Obese, no diabetes. No obese, diabetes. Like that, okay? Be careful that when you go to that table and compare, make sure that you're gonna read them very carefully from that particular table. See, here we have 0, 0 here. In the way that I have put 1, 1, okay? One can change that one, but so that if you're gonna do this one for the this is how that we were looking for that RR relative risk for the Cochrane, Mantle, and then Haenszel. One is HCM, HCMH. I'm gonna write and show you. Okay, is I'm gonna show this one for the one that you really need for risk ratio. Okay, you really need for this one, the bottom one. That's the one that we are expecting for, but I have presented here both. This one, you need this one. Okay, A1, D1 divided by N1. See, they are NI. NI means they are corresponding total. Okay, they are corresponding total. So AIDI. So this one. So see, this is for the gender. Doesn't matter which one we're gonna start from. That gender one for the female. So this for the female. If you write that one, I'm gonna write and show you. Okay. So it's gonna be 1. A means 1. Okay. 98,730. 98,730. D means 31, 476. No, 1. A means 1. 26, 20, sorry, 26, 26,271. 26,271. 271. Okay, 271. Then I need, it's D. D, I'm going to call the D for not 1. I'm going to call the D for 00. 98,730. 30 divided by its grand total 25,458. 25,458.7 divided by then B1 and C1 doesn't matter there. You cannot get the other diagonal. See B and C. See? So 5202 times 12 431 43381 divided by its grand total again 25 45 87. Okay, plus so this is what I'm talking about. That's for the male. See, that's for the female. So you do that one for the, go to the other table now. See, you go to this table. With the aid of this table, you do this cross and this cross. See, this one. See, 45. See, this diagonal multiplication. See, and over this one, and then the multiplication. Okay, if I add that one, this is for female plus the other one. I'm gonna get 45. Sorry, 4502 times 19,747 divided by grand totals 1644.24 over 3142 times 10,110.33 over 164,424. This is for that's what I'm talking about. This one, this ratio plus the other ratio you get. Then that's one called the relative risk score that it's been adjusted for the confounding by these three people, Cochrane, Mantle, and Heinz. I'm sorry, these are not relative OR. I'm sorry, OR. Okay, I used OR. OR one. Okay, that's the one we really need. OR one. You don't see. We don't need this one, but we keep in head. This is the one I used. Okay, that's the one they're looking at. Okay, do you see that value somewhere? Yes, we see that value. We see that one. See? So we ran this one. See, we told them to run this one. See, CMH relative risk as well. On the results there are, we see that one. We see the relative risk for each and every table as well. And their odds ratio as well. See. And here, where is that one? I'm going to see that one. Where is that one? Relative odds ratio with the wall confidence interval. See, here. See, odds ratio, Mantle Hansel. See, 3.367. Logit means instead of taking the odds ratio, you can get the log on that one. That's called the logit. Log on odds called the logit. Okay. Relative risk, Mantle Hansel one that you can do the column 1, column 2. We know that how to do that one. So, see, but this is the one that we focus on. See, 3.367. This guy. See, you should get this answer when you simplify. Mantle Hansel that odds ratio for the odds ratio. This one. Odds ratio, that one for that guy. relative one you saw too. And then later on, what they're gonna ask us to do. See? So each range diagram, and then we see then 95 confidence interval for interpret in terms of its width. Now show your calculation for diagnosing diabetes with respect to the obesity. You show that one. And calculation for the 95 OR confidence interval. See, interpret in terms of its width. Determine and explain if the OR are statistically. See, and that's the same thing. See? Obesity, you can do that one. See, OR that one, this one. Okay. Here, sir, here contingent table between this for each stratum. For the each stratum, you can separately do that one. I'm here, okay? I'm sorry, I'm here. Weighted OR with respect to obesity and interpret. I'm here. For this one, see, this one you're gonna say for the each stratum separately, you can just do the diabetes versus obesity, and you know how to write the confidence interval. For each one separately, you can do that one too. Separately, okay, not together. This is being put together here. Number part C is the one that I was showing over here. At part C, actually, this part C. I'm sorry, part C. Okay, Cochrane Mandrel Hensel is part C. Now part 2 is this one. Part 2. Sorry. Part 2. This one. Show your hand calculation for the OR, odds ratio for the diagnosis, diabetes with respect to obesity. Diabetes with respect to obesity, OR, you know how to show that one for each stratum, for male and female. Can you, in order to do that one, do you have the table? Yes. Do you know how to do that one? Yes. Not the Mantle-Hansel one, okay? The one that I showed you earlier in the beginning, OR, how to calculate OR odds ratio. That OR, that ratio for the male and female, you do separately. Can you write the confidence interval for those ones? See? Let's say that odds ratio on this one, that's a relative risk. This one, okay? You go to the that table, go to the male table, and do the this. See, calculate. Okay, go to the male table and calculate the odds ratio for male. Okay. That's what they say here. Okay, see here. And you do the same thing for female as well. Same thing you do for female, like the same way that we do, because those are not the same table. See? You're gonna roll the odds, then see. You get the odds. See? Then you go to the odds ratio. Sorry. Ratio. Or so what is the page before that one? Do we miss any page? Yes, here. I'm sorry. Here. Here. You wrote the odds and then odds ratio like that. And you got that one. That you're gonna do that one for your female table as well as the male table. You're gonna do this one for male table and female table. That's what we are expecting in that question number 2. Question number 2. That's what we are expecting. About yes, about up to here, That's what they, and they you do for the male and female as well for that one. And then I'll check that they are statistically different for each stratum, okay? Male and female separate. This is not a separation. You're gonna put pieces together. That's different setup. That's why they say it's more powerful. That's a weighted one. It's been weighted. Method, see, we are weighting that one. See, we weighted and we got that formula. See, that formula later on I show you how to do that one. See. That's the number. That's the number. Sorry, number 3. determine and explain if the sex is a confounding variable. Okay, that means if the OR, if OR do change over the stratum means like a through that your male and female, this referred to as an effect modifier, if not confounding variable. If not a confounding variable. See, to support to that one, I bring this one here. Okay. If the OR across two subgroups of control variable, whatever the our male and female in our gender are essentially the same as each, but are substantially different from the pool OR. See, estimated without the control variable. See, without pool, estimated without the control variable. See, then the control, see, that's the same thing we did. Can you remember? I told you to get the pool OR. Pool OR, see, estimated without the control. See, this example, sorry. OR1 for the one of the male and female like that, okay? And the pool one, if they were, see, if they were not different, see, if they not, see, or across two subgroups of corner essentially the same as each other but are substantially different from the pool OR, substantially. Then the control variable like to be a confound and we should use the CHM weighted average OR. This is because of the confounding. Whether it's a confound or not, how could you going to find? You separately find the OR odds ratio for this guy, male, female. Then how do you pool that one? Say the pool one. Where is that on the pool one? It's the pool one. I saw that earlier. It's been compared with that one. If they say that if it is a confounder, then you cannot use that OR. You have to go to that. So if that's the case, you have to go to CMH OR. Okay, we're going to come to that one. If OR across two subgroup of a control variable substantially different from each other, see? Oh, that sorry, that's the pool one. That's the pool one. Is the pool one is the one that we CMH one actually. It's a CMH. Pool one is a CMH. CMH one. It's a CMH. If they were, see, if they were same but different than this guy, you should go to this one. Then it's called the confounding variable that should be adjusted. See? You go to that one. That's the pool one. See? That's the pool one. See? Pool and weighted average. And sorry, the test for confounding, we can use the 10% rule applied to this one, which we might be very similar. But yes. If the OR across two subgroups of a control variable are substantially different from each other and are substantially different from the pool OR without the control variable, then the control variable likely to be confound and effect modifier. We should focus on the straight OR. And if the OR across two subgroups theta of a control variable are substantially different from each other but straddle the pool OR, straddle means they go to both sides. See? It's called the effect modifier. See, this is the OR. See, this OR. I'm sorry. Here is the pool OR. These two straddle. See, they go to both sides. See? Not in the one side. This one is what? This one confounding an effect modification. If they were the second setup, see, OR across two subgroups are controlled substantially different. Substantially different. Plus they were, see, the straddle across this one, straddle the pool OR, then it's going to consider it as a just effect modifier. To test for confounding, we can use the 10 rule applied to the pool and the CMH weighted average OR, which likely be very similar. See, they're similar because of they are the same. See, they are the same. And here, if OR across two subgroups for control variables, substantially different from each other, and now substantially different from the pool OR. They are different, and they are different from this guy too. Earlier, they were same and different from this guy. Here, they were different, and they were different from this guy as well. This one, they were different, and then they were straddled. See, straddle this guy. See. This look like they both build homogeneous. Yeah, that's the way that they can figure out that how they're gonna be like that. Yeah, or that simply that you can by looking at this one, see or do change over the statement. That's the same thing I was talking about. That go to each statement. See, so effect modify. If not a confound variable, simply you can talk like that one too. But more elaboratively, if you want to put the answer that this is okay. I want you to read this one. Yeah, here. Very clearly mentioned over here. So the effect modifier doesn't do any kind of any harm to that model, but the confound variable do such thing. So we have another test too. See, Breslow day test. We can talk about that one too. Okay, like that, roughly that. But we can add more to this later on, because that seems that I'm not going to fix that. Stick with the deadlines. You can take time and then that make everything complete and then turn in any time that you want. Okay, because I really want to jump into the other one too. Okay, that's why roughly that get rough idea. More elaborated we can talk about later. See, it's a confound or effect more variable based on that the properties. See? So this one, you know that roughly that you have a rough idea how to get this done now. Okay. And then you have a program, whatever the programs you really need to do that one. And let's look at that in-class assignment a little bit. Okay, with those two. That's the in-class assignment. Here, I'm sorry, here. See, a pharmaceutical company gives you like a data set and asks you whether its new medication is better than placebo. They provide you the following statement. Dear data analyst, our clinical trial from 160 individuals resulted in the following. The new medication was favorable in 51 individuals and unfavorable in 31 individuals. The placebo was favorable in 27 individuals and unfavorable in 59 individuals. Could you please provide us a contingency table as the first step for our next report? Create a SAS data, name, autism, that contains three variables. A variable containing the value of treatment, a variable containing the value for the outcome is the treatment. See, that's the treatment. See, same way that I was talking about earlier. When we build up this table, see, like here, see, the risk side is outcome. Okay, risk for that whatever the medication status. These are the outcome on this side. Okay, so that variable, and then plus the variable contain number of observation. Create a contingency table. Test whether the new medication is effective. How strong this relationship would be. OR. See, based on OR and RR, you have to fill this out. So how could you gonna get this done? Okay, let's go ahead and look at that. Let's build up the R codes for this one. See. Okay, see, I'm going to call that one data. They say to call that data. See, autism data. See, it's going to go to the work group directory. Inputs. You can give the inputs. Treat. See, treatment. I'm going to call treat. Outcome. I call outcome. The number of observation. I'm going to call the count. And then I built up. They gave all the information. See, when we based on the information here, they see new medication was favorable in 51 individuals. See, 51 individuals. If you put the 0, 1, 0, 0, 1, 1, 1, 0, so this one, see, treatment outcomes, see, based on that one, you know that the treatment means like the medication. The 0 means 1 means medication, 0 means placebo. So the if it's a medication, see, 51 individuals are unfavorable. Sorry, individual favorable. Okay. Medication favorable. I'm gonna say 1 for the favorable, 51. So see, and 31 individuals unfavorable. Medication, see, you give the medication but unfavorable. The other one placebo, favorable in 27. Placebo, but favorable. Now placebo, then the 29 individual, could you please see, individual gonna be unfavorable and placebo, see, like that. Then question number 2, what they ask us to do, that create a contingency table. See, if you want, you can sort this out by descending or ascending order. See, and then get the work autism order data. See, weight count table. See, treat by outcome. Let's get this data on first, and then like that. So continuous table. If you don't like these percentages, you know that what you're supposed to do. Okay, you can get rid of them. See, by telling that no column, no rows, no percentage, like that. And test whether the new medication is effective. How could you gonna test? This is number 1. I'm sorry, this is number 1. How do you test? Test whether the new medication is effective or not. What are you gonna do? Put data, so results. Whether the new medication is effective or not, you can get, what do you get? Number 3, see, I just formatted this one in another way, test placebo, favorable or unfavorable, and then I'm going to run chi-square test, relative risk, and then no percentage and all kind of stuff. See, you have a odds ratio setting, you have a chi-square test. See, this one you have its corresponding p-value. Don't go to this test yet. Okay, go to chi-square test. You know, there's a correlation between those two. Tests would be that what? There's a correlation between what? Correlation, association between, the medication and the outcome. Outcome means whether that medication being favored or unfavored by the people. So that can be tested. You have to write the okay, testing test is not blah blah like that. Yeah, as of now, you know how to do that one. How strong in the relationship? What measure of association strength can be used? How do you check this relationship? That's all. The odds ratio, relative risk. You can utilize those ones. Odds ratio. See, people who are favored. See, this is nothing but the people who favored that the drug is 3 times more than that who didn't have that drugs, who got the placebo. The favored with the people who had the drugs versus the people that who got the placebo. So that means like it's a 3 times higher. See? Favored by these people that who had a drug is 3 times higher than those people who had the placebo. See? Yes, you can explain that one. The association The association strength can be measured by the odds ratio or relative risk. Okay. And using the estimated value, see, using the estimated value, see, using the estimated odds ratio, fill in the following statement. The odds of the patient receiving the medication is having favorable outcome. See, 3 times. See. See. This one here. So you can fill that relative risk with the aid of the relative risk. One of the relative risk should be gonna go there based on your table. Okay. Because read very carefully, they were patient receiving the medication having favorable outcome to the patient receiving the placebo having an outcome. So you have to make sure that you want to go ahead and read the table, the right cell, the correct cell. Want to make sure that you're going to read the correct cell. Like this. So let's like this. You read this one. See. What test? Sorry, here. Let's go. This one. What test? This one. What's test? Odds for this guy, odds for the placebo, or R has been already given. You don't have to calculate. You see the table here. See, you don't have to calculate. Another table you can see 3 times greater than patient. The relative risk. Make sure that which relative risk you're going to take into account. This or that. Okay. This one related to the table. See favorable table. See this one column 1. So go to the column 1 2 times. Right there. If you want, you can calculate and then see whether it's going to be right or wrong, whether this is going to produce a right answer. See, and check. See? Risk test, risk variable, then relative risk. Then you can say the risk. You can give the other way around for the second column too. This one, the risk for favorable ones. This is for the favorable one. Unfavorable one, again, you can give another one. Risk test for unfavorable. That's going to be what? 50, sorry. It's going to be 31 divided by 82 over 59 divided by 86. That's it, very easy. Once you get the rough idea, it's not a big deal. Look at it, the second one, the second test. Second one. The pharmaceutical company gives you a data set and asks you whether it's a new medication for acne is better than its old medication. They provide you the following statement. Dear data analyst, our clinical trial from 2016 individual yielded the following results. Regarding the females, the new medication showed positive results in 43 and none in 17. The old medication showed positive results in 35 and none in 30. Regarding males, the new medication showed positive results in 29 and none in 18. The old medication showed the positive results in 23 and none in 21. Could you please provide us a frequency table for the cross classification and 2 more frequency tables controlled by 6 as the first step to our next report? Create the data, acne, that contains data name, acne, that contains the 4 variables. Variable containing the for the gender, treatment, improvement, and observation. Okay. Right. So for that one, you know how to do that one. So you need a gender. No, you really need a gender one. Okay. It's going to be 1 and 0. Next one is a treatment. Treatment would be whether treatment and medication show the positive result. Regarding the female, the new medication show the positive result in both ways. The old medication, see, medication treatment. See? Treatment means new and old. Okay. So they say, let's go to the other one, outcome. Positive results or negative results, positive or negative results, how many? Let's say let's do it regarding the females. Females were denoted by 1. New medication is 1. Treatment is 1. And positive results is 1 is how many? See, 43. Based on the given description, you can build up your data set. See? And build up the data set. Then create a frequency table for cross classification. Tables, treatment and orders. Count. If you want, you can get this one. Outcome and treatment. See, with the treatment, see, outcome is, it's been positive results, negative results, positive, positive. See, the new one is the old one. Test whether the new medication is effective. You know that how to check that one. So you can get the for that one thing. Number 3, see, we can make it more elegant and generate chi-square or blah blah everything. See, the treatment format, you can format. See, new medication, all medication, positive, none. Okay, female, male, like that. See. Outcome all see, they can see clearly that clearly like that. You have a odds ratio, you have a relative risk, then you have a chi-square. See, whether that this is effective or not. Effective or not means like a definitely you're gonna run and see there's an association or not. Then chi-square test. That's the chi-square test. See. So number 4 and test whether the new create a new frequency table controlled by sex. Okay, that's number 3, 4. The number 3. Sorry, number 3. The number 4 using the estimate odds ratio and everything you can fill in that table. Okay, fill in that table. Then number 5, create a 2 frequency table controlled by gender. You know how to do that. But see, you can do this way too or this way. Okay, either way. Okay. 7B. 7. No, create a frequency. I'm sorry, I'm looking at the wrong place. Create a 2 frequency test whether the new medication effective differs by sex. Okay, create 2 frequency table would be number 5. 2 table is create a 2 frequency table controlled by this. I'm sorry here. Okay, that's right. Okay. The number 4, number 3. Yeah, number 5. Yeah, create a 2 frequency controlled by and the test whether the new medicine is effective differ by sex. The test whether the association between the treatment and outcome differs by the statement. That means in the gender. Can we do it to specifying the sex in the table statement or run in prop frequency by sex? The advanced format is your get full graph. Okay. Okay. So you can do it this one. See. It's talking about you're gonna get see for the male and the other one for female. See. One for male, one for female. Table female, this one. Sorry. This one for male. That discussion we talk about earlier. At 5, then 6, test whether the new medication is differ by 6. You can check that one. You see the odds ratio 7 and 8. See? 8 is the one that see, if you want you can calculate by hand or you can get this one. See? Same thing. 7B. How confident should be in this page? OR is calculated for female and male. Okay, affected by this number 6. This one. Number 6 and number 5 and 6. This one. 5 and 6. Okay. This one is 7. This one is 7. 7 that 7 that's the same thing. You can use the same table. I'm showing that it can get it done in another way. It's the same table. With the aid of that table, you can answer 7. and then 8, 8, 8, you get this guy, see, CMH. That's the same. Or by doing by hand. You don't have to see. Okay, here. This one. They get there, see, this one, and then plus something that I want to show you. That, yeah, that one. It's the standard data. Yeah, that's the part they don't ask for that. I don't think the confidence interval. We don't need the confidence interval for this. Just this value only that we ask for. We can talk about that one too later on too. That more adding more since that because of the too much that I don't know. Because that's why I'm expecting you to do the same thing we use in R. If you cannot get this by R, see, look at this in R. Oh man, sorry, this one. It's not the one. Yeah. You can try and then see that how could you gonna do that. This not this for the homework that I did over here. That homework one here. See? You try and see. And the other, yeah, that's the mainly that that we can continue the same discussion that again next Monday and then move on to that other stuff and then let's see that how much of the material can be covered and based on the next that homework assignment. Okay. So I plan to wind up over here. Do you guys anything to discuss? Or the mainly that I'm gonna talk about that the project starting next week. Okay, then I'm gonna give you like some help for you to that come up with a nice presentation and the report at the end of the day. I think first day I mentioned that if you really wanna that use the LaTeX, use some template and then go to the overleaf. I think I broadly talk about that on first day. So using LaTeX that you can give like a nice report that and that that kind of a practice you can carry to when you're going to do that capstone project at the end of the day. Because that I'm mentoring 2 students right now, and I told them to that do everything everything you can get it done everything by one shot because that if you use LaTeX because by changing that format a little bit you can get the presentation we call the beamer and the other one is a research the report plus that report we can send to easily if you're going to use like some kind of some journal format easily send to a journal and then get publication. So that's the target at the end of the day. That's here we are just laying down a kind of that kind of foundation by assigning that kind of a project at the primary stage. But even at the primary stage, if you're going to go ahead and use those kind of software, more sophisticated one, that's going to be very beneficial down the road. So anyhow, that I help you out, you guys, to come up with a nice research report, the paper report, and that this one. Or on the other hand, if anybody is interested in doing research or publishing journal, let me know because I'm doing research in a large scale. That's my major that interest. So let me know that if you guys need any help on that one. Okay. So do you guys have any questions? If not, what I plan to do, I'm gonna just go ahead and then stop over here and then we continue the same discussion again till Tuesday and then go move on. Okay. You guys have a good night and have a nice weekend and see you next week. Okay. Stay safe and be well. Take care.
Thank you. Good night,
Thank you,
Professor.
Professor.
Have a
Good
good
night.
night.
Thank you very much. Take care. Take care. Right.